All right, welcome everybody. I'm Hanpu. I'm a theoretical atomic physicist in the department, so I'll be representing our AMO program and introduce our very dynamic AMO program in our department. So AMO physics is to study atoms, molecules, interactions between them with light, and etc. So and we know that this year is actually the 50th anniversary of the invention of laser, which played a very important role in AMO physics and in many other branches of physics. And atomic physics in recent years has been very active, and in recent decades we have atomic physics and optics. Quantum optics have won 3 Nobel Prizes in laser coolant trapping, quantum atomic bosons decondensation, and quantum optics. And at Rice, so the Rice AMO program is one of the top programs in the US. It's ranked among the top 10 in recent rankings. And our programs are so these are the areas, the research topics that have been conducted in we have 5 groups, which I will introduce later. And so we are heavily focused on optical atomic physics. So we study laser-cooled atoms, quantum degenerate atomic gases, for them to condensate, or degenerate Fermi gases. And also ultra-cold plasmas, which are the kind of plasma which is very different from the plasma we just heard about. And also nonlinear dynamics immutable atoms. So these are the atoms that have been excited to very high principal quantum numbers. And so right now we have about I think more than 20 graduate students in 4 or 5 groups. We have quite a few postdocs, and we also have many undergraduate students working with us doing their senior thesis or just doing a summer internship. And we are affiliated the cold atom groups are affiliated with the 2 research centers within the department. One is what we call the Laboratory for Optical Physics. That includes 4 groups that are working on optical atoms. And this is a program funded by Keck Foundation. This is the Laboratory for Quantum Magnetism, and this is a joint entity between the AMO groups and also condensate groups. So here are the people that are working on AMO physics. Barry Dunning is the chair of the department, who you have met already earlier today, and he's working on these highly excited Hilbert atoms. And Randy Hewlett and Tom Killian are 2 experimentalists working on optical atoms. And I'm the theorist. Professor Ivan just joined our department last year, and he is actually, his background is condensate physics, but he many of his research topics are in optical atoms. So I think Professor Julia will introduce his research. So yeah, all these 4 groups are working on optical atoms, which in recent years is not just is one of the most active areas, not just in atomic physics, but also in all physics. And so one of the reasons we study these optical atomic physics is the unity of all physics. So by studying these very cold atoms, where the temperature is on the order of microkelvin, so it's really, really cold stuff. But by studying these very cold atoms at very low energy scale, we can learn something that is much hotter. For example, the electrons in metal, the superconductors, or even the nuclear metal emits a neutron star, which is 18 orders of magnitude hotter than these cold atoms. And these different systems, well, apparently they are very different, but the beauty of physics is there are many common physics that underlie all these different systems. So by studying the cold atoms, you can actually learn something about a neutron star. And cold atoms can be very easily controlled and manipulated in the lab, whereas neutron stars, you cannot do much, and they live in space, and we do not have much control. So, optical atoms is actually a very interdisciplinary area. It has a connection to many other branches of physics, and to the extent that some people call optical atoms is actually out-dilute solid-state physics. So